Hello friends, today we are going to solve the question from the year 1986, and 1986 consists of one question. 1987 total there are three questions. From the year 1988 we are having one questions, and from the year 1989 total number of questions are two. So in totality we are going to solve 7 questions. So in the first question, which was asked in the year 1986, and it states that a part of a circuit in steady state along with the current flowing in the branches, the value of the resistance etc. is shown in the figure. Calculate the energy stored in the capacitor C, whose value is given as 4 microfarad. So circuit is given to us, which consists of only one capacitor and a network of resistances, and various values of current are also given in it. But here the important part is that we have to discuss this solution under steady state condition. And under steady state condition we are mainly interested in the behavior of the capacitor. Okay. So it means at steady state you can see at steady state condition our capacitor will be fully charged, so there will be no current flowing through the capacitor, or we can say that capacitor is going to act as a open circuit. So we can say that at steady state, first is that capacitor is fully charged, is fully charged. Secondly, we can say that no current through the capacitor, no current through the capacitor. Or finally we can say that capacitor acts as an open circuit, acts as open circuit. Therefore we can just redraw the figure. Okay. And here we are not going to draw the battery etc. because the value of the currents are given to us, so we are not interested in this 4 volt as well as 3 volt. Okay. So the value of the resistances are given as 3, this is also 3, and we have a 5 ohm, and then 1 ohm, 2, 4, this is also 3, and this is 1 ohm. And the value of the current that is given to us is, this is 2 ampere, 1 ampere, and here also we are given as 1 ampere, and it is our 2 amperes. And let us provide alphabet for the circuit, and we call this as, let us suppose this is our A, B, this is C, D and E, F as well as our G. and the capacitor was our open circuit. So this was our B and D, and capacitor was somewhere here. So this acts as a open circuit. So no current will be flowing through this. And we can find out the various values of the current that will be flowing in the circuit. I think one part, okay, we'll see that later on if required. I think one value of the current is missing in the main circuit. I'm not sure about it. We'll check that later on if required. Otherwise, we'll sort it out. And let us suppose the current that is flowing from here, we call this as our I1. And if we use our KCL at node B, okay, so we can say that Kirchhoff's current law at node B, incoming current is our 2 plus 1 will be equal to our outgoing current, that is our I1. So we get our I1 is equal to our 3 ampere. Okay. And the current that is flowing through here, let us call it I2, and that I2, I think here, yes, the value of current that is flowing through here is a 2 ampere. It is missing in here. So this is given as 2 ampere. Okay. And we can use our KCL at node C and find out the current. So you can say KCL at node C, incoming current is our I1, that is our 3 ampere. So we can say I1 is equal to I2 plus outgoing, that is 2 ampere, and our I1 is 3. This comes as 3 minus 2 is equal to I2, which gives us that I2 is equal to our 1 ampere. Okay. So we found out the value of the current I1 as well as the value of the current I2. Okay. Now we can use, you can say, our Kirchhoff voltage law, and for the Kirchhoff voltage law, suppose that is our B, let us call this as B prime, that is our B, B prime, C, D and B. So you can say our Kirchhoff voltage law, and the loop is our B, B prime, C, D, and we come back to our B. And the current is flowing, okay, let me draw the loop separately, it will be much more convenient. So this is our B, B prime, C, and this is our D. We have 5 ohm, 1 ohm and 2 ohm, and the current, this is our 3 ampere, and here we get it as 1 ampere. Okay. So obviously the current through 5 ohm is flowing from left to right. Okay. Direction of the current is from left to right, and current flows from higher potential to lower potential. So this will be plus and minus. Similarly, through 1 ohm we are going to get plus and minus, and once again from 2 we are going to get plus and minus. Let us suppose we use the loop direction as it is. And so we can say that that is a fall in potential. So fall in potential we are going to take as negative. So this will be minus 3 into 5, and then we have our plus, once again minus 3 into 1, and once again our plus, and this is our minus 1 into 2 will be equal to the potential at B. Let us suppose we call this as VB, and at D we call it as our VD. So we get here from this will be our VB and VD. Okay. Let's so we can write this as our VD minus VB, and we get this as minus of 15 minus of 3 and minus of 2 is equal to VD minus VB, and this comes as minus 20 minus 20. So we can write this as will be equal to VB minus VD is equal to 20. So it means this is the potential drop across the capacitor, okay, because here we were having a capacitor. So you can say this is the potential difference across capacitor, and we need to find out the energy through the capacitor. So we can say that energy stored in the capacitor this is comes to half C, and we have this as VB minus VD and its whole square. We substitute the values. This is comes as half 4, and with this have a 20 minus 6, and this we have a 20 square. And if this energy is given as U, so we can say this U will be coming as 8 into 10 to the power minus 4 joules. So this is the amount of energy that is stored in the capacitor. Next question. It states that it was asked in the year 1987 and states that 3-point charges Q, 2Q and 8Q are to be placed on a 9 cm long straight line. Find the position where the charges should be placed such that the potential energy of this system is minimum. In this situation, what is the electric field at the position of the charge Q due to the other two charges? So it means we have to find out the potential energy of the entire system should be equal to minimum. Okay, and the system consists of these 3 charges. Okay. So there will be, we can say, the energy because of the interaction of the charges Q and 2Q, then it will be 2Q and 8Q, and the last one will be 8Q as well as Q. Okay. And we know that the potential energy of a 2-point charges is given as Q1 multiplied by Q2 divided by 4 pi epsilon naught and divided by R, where R is the distance between them. Okay. So it means for a minimum potential energy, the value of R should be as great as, you can say, large as possible. Okay, so they should be placed farthest from each other, all the charges. So we start from there only. So we say that potential energy of a 2 point charges separated by R is given as U is equal to 1 upon 4 pi epsilon naught Q1 Q2 divided by R. 2 point charges here are Q1 and Q2. So it means to have a minimum potential energy, the charges of greater value should be farthest apart. So you can say minimum potential energy charges of greater value should be farthest apart. So here we are mainly interested in 2Q and 8Q. Therefore, from here we can draw one important conclusion, that because the entire charge system is to be placed on a 9 centimeter long straight line, and we need that 2Q and 8Q should be farthest apart. So it means at one end of the straight line we should be having 2Q, and the other end we should be having the 8Q. Okay. So charges of the greatest value should be farthest apart. Therefore, 2Q and 8Q should be at the extreme end of the straight line. Extreme end of straight line, or we can say that is distance is given as 9 centimeter apart. 9 centimeter apart. And from here we can also draw one important conclusion, that charge Q should be between 2Q and 8Q. So therefore we can draw an approximate figure now. We have our 2Q, and other end we have our 8Q, and they are at a distance of 9 centimeter. Okay. And for the sake of convenience, let us say we represent this distance as D, and we have a third, that is of Q. Let us suppose it is somewhere here, and it is at a distance of x from 2Q. Obviously from the other end it will be our D minus x. And now we can find out the potential energy of the entire system. So we can say potential energy of the system, that is our U, and one parameter, that is our 1 upon 4 pi epsilon naught will be our common. First we can say the interaction of 2Q with Q. So this comes as 2Q multiplied by Q divided by X, plus then we can write interaction of 8Q with the Q. So this comes as 8Q and Q divided by D minus X, and plus finally we have our 8Q and 2q divided by d. And we need that this u should be equal to minimum. Therefore, we can say its derivative should be equal to 0. So we can say u should be our minimum, or we can say du by our dx should be equal to 0. So we can differentiate it, and differentiation is going to give us minus 2q square, and we have a x square plus, and we have this as 8q square, and this will go d minus x whole square should be equal to 0. Now it is quite simple calculation. It gives us that our we can take 2q square as common. Obviously 2q square cannot be equal to 0. Therefore we get from here that our, okay, let me sort it out directly. 2q square upon x square is equal to minus 8q square upon d minus x whole square. And this minus and minus goes away, and this goes by 4. Q square, we can also sort it out. Otherwise we can say taking q square as common, which cannot be equal to 0. So from here we get that our d minus x whole square should be equal to 4 times x square, or we can say that our 2x should be equal to d minus x, and we can say that our 3x should be equal to d, or we can say x is equal to d by 3, and d is given to us as 9. Therefore we can say our x is equal to 9 by 3, which gives us that x is 3 centimeters. And so we found out our x. So distance of q from 2q is our 3, and from other side obviously it will be 6. This will be 6, and this we got as 3. And second part, we need to find out the electric field at the position of charge q due to other two charges. Okay, so we need to find out the net electric field. Therefore we can say that net electric field at charge q will be, if given as E, will be equal to 1 upon 4 pi epsilon naught, and this comes as 2q divided by 3 square minus 8q divided by 6 square. And we can take common, so we get our electric field is equal to, we take 2q as common, so this comes as 4 pi epsilon naught, and here we have 1 upon 9 minus this comes as 4 upon 36, and this comes as 9, and 9 cancel with 9, so we get the value of electric field is equal to 0. Next question, it states that it was asked in the year 1987, a parallel plate capacitor is charged and the charging battery is then disconnected. If the plates of capacitor are moved further apart by means of insulating handles. So we have to find out how the charge, voltage, capacitance and electrostatic energy is going to change, whether they're going to increase, decrease and something like that. So initially we can just divide into two parts. So initially we can say we have a capacitor and connected to some battery voltage source, and then later on we remove the battery source. Now the capacitor is something like this, and then the distance between the plates of capacitor is increased. Okay. So this is the basic question. Okay. And after the battery is removed, let us suppose this is the voltage V, the charge on the capacitor is going to remain constant. That will be our Q. Okay. And if A is the area and D is the distance between the plates, therefore we can say that charge on capacitor remains constant. After disconnecting the battery. After disconnecting battery, which is our Q, and the capacitance of a parallel plate capacitor, that is our C, it is given as epsilon naught A upon D, and D is the distance between the plates. D is the distance between plates. So obviously as D increases, capacitance is going to decrease. We can say what D increases, this results in decrease in the capacitance. But we have to remember that the charge is our constant. Therefore, we can say that our, if initial capacitance is our C1, initial capacitance is our Ci, and initial voltage is, let us suppose, Vi, and we have our final capacitance let us suppose that is given as Cf, and final voltage is our Vf, but our charge is constant. Therefore we can write that the product of C initial, V initial should be equal to C final and V final. Okay. But we know that our C initial means, C final means that when the distance has been increased. So obviously C final is our less than C initial. From here we can say our V final will be greater than V initial. So it means voltage increases. So from here we can say that our voltage increases. And next is our energy, potential energy, that is our energy stored, that is U, is equal to half Q multiplied by V. So from here Q is a constant, so we can say our U is directly proportional to V. So we can say our U initial is directly proportional to V initial, and our U final is directly proportional to V final. And we just found out our V final is greater than our V initial. Thus we can write that our U final is greater than U initial. So it means the energy also increases, potential energy increases. Therefore option number D is the correct one, and charge is same, voltage across capacitor increases, whereas voltage across capacitor increases. Okay, so our B is also correct one. So B and D are the correct options. Option B and D are correct. Next question. It states that it was asked in the year 1987, a charge Q is placed at the center of line joining two equal charges, capital Q. The system of three charges will be in equilibrium if Q is equal to. Here also the entire system of the three charges should be in equilibrium. And it states that we have a state, you can say three charges, and two extreme charges are capital Q and capital Q, and at the center a small q charge is placed. So if x is the distance between the two charges, capital Q charges, then at the center will be x by 2 and other will be also our x by 2. And we need that the entire system should be in equilibrium, or we can say our net force should be equal to 0. So let us consider this as A, B and C. So let's find out the forces at charge point C. You can say forces at charge Q, which is at point C, and for the equilibrium the net force should be equal to 0. It means force due to the charge A on C and the force at charge B on C should be, their summation should be equal to 0. Therefore we can say that force because of charge A plus force because of charge B should be equal to 0. And we just substitute the values now. We get 1 upon 4 pi epsilon naught. We can take that as common, and our FA will be equal to capital Q, and that will be our Q square, and divided by x square, plus, and this comes as Q, capital Q, and we have this as x square by 4 should be equal to 0. So from here we can take few things common, and we can write this as 1 upon 4 pi epsilon naught. Capital Q we can take common, we can also take common as our x square. So we are left with Q plus 4 times small q is equal to 0. So obviously second term we can say our q plus 4q should be equal to 0. This gives us that our small q is equal to minus capital Q divided by 4. So we get minus, option B is the correct one. B is correct. Next question. It states that three particles, one second. Okay. It states that the three particle it was asked in the 1988. Three particles, each of mass 1 gram, carrying a charge Q, are suspended from a common point by insulated massless string, each 100 centimeter long. If the particles are in equilibrium and are located at the corners of an equilateral triangle of each side 3 centimeter, calculate the charge Q on each particle. So we are given that we are having three charges, and these three charges form an equilateral triangle, and these individual charges are hanged by a thread to a common point. So we can just draw an approximate figure for that. So we have a three charge system, and they are in the form of equilateral triangle. So let us say that we have this as a three charge system. This is our A, and let us call this as our C, and this point as our B. So these are the three charges, and they are hung from a common point. Okay. So let us suppose this is the common point, and they are connected something like this. This common point, let us call this as our P. This is equilateral triangle, let us call this as side as A, and the length of the string with which it is connected, let us call them as L. And this is an equilateral triangle, so obviously each angle will be of 60 degree. And let us, you can say, draw so this, and let us join P point to here, and this angle will be about 90 degree. Let us call this as height as H. And the angle made by this height with respect to one of the side is, let's suppose, theta. So therefore this angle will be also called theta, and everything we can say is just in an equilibrium. So we can consider any one of the charge and solve all the forces for that particular charge. And for the sake of discussion, let us assume we are discussing charge A, and there will be a force acting in downward direction, that will be over mg. And all these charges are, you can say, same, so they are going to repel each other. Let me call this as point A, somewhere here. So B is going to repel A in this direction. Let us suppose that force is a F, and C is also going to repel A with the force in this direction, which will be obviously equal to A, because the distance between the charges are same and the value of the charge is also same. Okay. So therefore this will be our basic, you can say, figure. Okay, and we can also specifically for this point A, let me draw another figure, and let us call this as point as O. So this is our A, and we have a, this is point O, this is our point P, and we already know this angle is given as theta, and we have called this height as h, and this angle is about 90 degree, and this is our point A. mg will be acting in downward direction, this angle will be about theta, and there will be tension T in the string, and the length of the string is given as L. And obviously the net force from these two, we can also make an you can say approximate guess that the net force will be acting towards the left side. So this will be our net force. So here let me redraw this. It will be something like this. And in order to find out this net force, and please remember that, okay, let us call this as figure A, this is our figure B, and in order to find out the net force that will be acting on charge A, we need to draw only the charge which are based on the triangle. Okay, so we need to draw another figure which is a equilateral triangle and consisting of only the charges, because the force is respectively only because of the charges. So we, this is our C point, this is our B, and this is our A. Okay. And from B to A, this is force F, and we have this as our force F because of the C. And let us call this point as D, and this angle will be over 30, and this angle will be also over 30, and each side is equal to over A, because this is our equilateral triangle, and this angle is 60, and this angle will be also 60. So we can divide our forces into the components, and so one component, this angle is over 30, so we are going to get this will be our F cos of 30, and the other component will be, one second, is it the correct one? Sorry, not. So let us call this as first part, second, and it will be like this. Yeah, this will be two components. Okay, so this will be of F sine of 30, and this will be over F sine of 30. And there will be two forces lying on the same direction. One will be F cos of 60, okay, because this angle will be over 30, and other one will be also over F cos of 30. So this will be over 60, not 30. Sorry, one second. 30, 30, 30, yeah. So this will be over 30. So F cos, and here also we get our F cos of 30. Therefore, the F sine and F sine are going to balance each other. Therefore, we can write our F net will be equal to 2F cos of 30. Let us call this as figure C. So we have almost drawn all the required figures, and let us okay, and here for tension, so this will be over T, and we get this as sine of theta, and this will be over T cos of theta. So from a figure B, we can say our F net will be equal to T sine of theta, and mg will be equal to T cos of theta. So from figure B, we can say that our mg T cos theta is equal to mg T cos of theta is equal to mg, and we can say our T sine of theta is equal to our F net, and F net we just found out is 2F cos of theta, cos of 30, sorry, not theta. And if we divide these two equations, let us show this equation 1 and equation 2, we can say from equation 1 and 2, from equation 1 and 2, we can write our tangent of theta will be equal to 2F cos of 30 divided by mg. And we substitute value of cos of 30, and that comes, so we get from here that our tangent of theta will be equal to, this will be root 3 by 2, so this comes as root 3 times F divided by mg. And we also know that the force, you can say, between two charges, you can say that force F is equal to 1 upon 4 pi epsilon naught. We have charges are same, and distance between the charges given as a, that is our a square. And we can also say our tangent of theta, that is in triangle, this is our PAO. Okay. So we can say tangent of theta will be equal to OA upon OP. Okay. And OA, let us suppose we get this OA, and we are left with our OP. OP, we can say that is equal to L square minus AO square square root. So here we get our L square minus AO square and its square root. Okay. And we can also say that our OA, because it is a from figure A, we can say this distance OA, we can say our OA is equal to 2/3 of AD. Is 2/3 of AD. Oh, sorry, I forgot to mention point D. Yeah, so this is point D. So here, let me draw it. This is point D. Okay, so OA will be 2/3 of AD. So we can use relationship. So we can say that our OA is equal to 2/3 of AD, or AD, we can write this as 2/3, and AD will be equal to over A sine of 60, which comes as A square root of 3. Therefore, we found out our OA. Now we can easily find out our tangent of theta. So we can say our tangent of theta will be equal to OA is our A square root of 3 divided by, we have this L square minus, this comes as A square divided by 3 and its square root. And this length L is very much greater than our A. Therefore, we can say that our tangent of theta is approximately equal to A square root of 3 times L. And if we substitute the value of F as well as tangent of theta, so we can write that our tangent of theta we just found out is our A square root of 3 divided by L will be equal to, and this comes as L, we already, one second, yeah, so let us call this as equation number 3. So using equation 3, and that is our tangent of theta is equal to square root of 3 F divided by mg, and we substitute here tangent of theta and the value of F. F we already know, tangent of theta we just found out. Therefore, we can write this as A square root of 3 times L is equal to square root of 3, and we have mg, and force was equal to 1 upon 4 pi epsilon naught, and q square upon a square. we are only interested in finding out the charge, that is Q. So we just manipulate the equation and we can write the ever charge Q is equal to, this comes as A cube. So we can write this as 4 pi epsilon naught. We have A cube and this is mg. 3 square 3 is comes as 3 multiplied by L, and this comes as whole 1 by 2. And all the values are given to us. Okay, so we simply substitute the values and we can get the answer. So we get to, this is 9 into 10 to the power 9 multiplied by 3, and length is given to us as 100 centimeter, and triangle length is given as 3 centimeter. Okay, so we have 100 centimeter into 10 to the power minus 2, and we have this as mass is 1 gram, so this is 1 into 10 to the power minus 3, 9.8, and we are left with only A. A is our, is given to us as 3 centimeter. So it means 3 into 10 to the power minus 3. 3 into 10 to the power minus 3 whole cube. Sorry, 3 into 10 minus 2. And this comes as 1 by 2. Okay. So we get that value of charge Q will be approximately equal to 3.13 nanocoulomb. So this is the value of the charge. Okay, this question was, you can say, straightforward, except that the visualization of all these three figures, this is the most critical part in this entire question, because if we are able to visualize all these three figures A, B and C, the solution is quite straightforward, because then we are only going to balance the forces. Next question, and it states that it was asked in the 1989, and it states that we have a solid conducting sphere having a charge Q is surrounded by an uncharged concentric conducting hollow spherical shell. Let the potential difference between the surface of the solid sphere and the outer surface of hollow shell is V. If the shell is now given a charge of minus 3Q, the new potential difference between the same two surfaces is. So here inside we have a solid sphere. So let us draw an approximate figure. So we have a solid sphere. Let us suppose the solid sphere is having a radius R1 and it is surrounded by a hollow shell. And the radius of hollow shell is, let us suppose, given as our R2. And we have to find out what will be the potential difference before and after. Okay, before means when there is a charge only on the sphere, that is capital Q, and later on the shell is also given a charge of minus 3Q. So we have to find out how the potential difference is going to change. And we know that the voltage so we consider a sphere of radius r1, and we have a shell of radius r2, and we know that the potential of the sphere, or we can say the shell, will be equal to, let me write it down, we can say that potential due to sphere, let us suppose that is given as V1, which will be equal to K charge on it and its radius, that is our R1, and the potential due to the, we can say, shell, potential due to shell let us call that as a V2, and that will be equal to KQ upon our R2. And it's quite easy to understand how the charge will be Q, because it is having a plus Q, capital Q rather. So the inner will be our minus Q and outer will be our plus Q. Okay, so this will be because of the induction. Okay, so that's why the potential, because the charge on the this shell will be also equal to Q, and we can easily find out the potential difference. So you can say the potential difference which in the first case is given as V will be equal to V1 minus V2. We substitute the value, we get KQ as will be constant, and from here we are going to get 1 upon R1 minus 1 upon our R2. And when charge minus 3Q is given to the shell, minus 3 capital Q, minus 3Q is added to the shell. So because of that, we can say the potential at the surface of the sphere. Okay, potential at the surface of sphere. Let us call that potential at V1 prime. So V1 prime will be equal to, this will be our KQ upon R1 minus K3Q upon R2. Okay. And the potential at the surface of shell, let us suppose that is given as V2 prime. Potential at the surface of shell, and let us call that V2 prime will be equal to KQ upon R2 minus, this is K3Q, and this comes as minus of R2. We have to find out the potential difference. So therefore we can say that the potential difference, let us suppose that is our V prime, will be equal to V1 prime minus V2 prime, and we simply substitute the value. We get this as KQ R1 minus 3KQ R2 minus KQ R2 plus 3KQ upon R2. This 3K and 3K cancels out, and we get that our V prime will be equal to KQ 1 upon R1 minus 1 upon R2, and the right hand side is nothing but equal to our V. Therefore, we can say our V prime is equal to V. Therefore, option number A is the correct one. Option A is correct. Next question. It states that it was asked in the year 1989, and it states that the capacitor C1 of capacitance 1 microfarad and capacitor C2 of capacitance 2 microfarad are separately charged fully by a common battery. The two capacitors are then separately allowed to discharge through equal resistors at time t is equal to 0. And accordingly, we have to find out how in the first three options, how the discharging current is going to behave, and the final option is about the loss of initial charge. Okay. So we are given two capacitors C1 and C2. So we have C1, and initially they are fully charged by a common battery. So we are only going to draw the figure for their discharging through a common resistance, that is R, and same is for the C2 also. R. So this is plus minus plus minus, and the values are different. C1 is of 1 microfarad and C2 is of 2 microfarad. And discharging current in a circuit, the general formula, if we are having capacitance C and resistance R, so the discharging current in the circuit is our I is equal to I naught e raised to power minus t upon RC, okay, where I naught is our initial current. Where this I naught is our initial current, and that value equal to our V upon R, and here V is the potential with which the capacitor is charged. Potential with which capacitors was charged. And because they are fully charged by a common battery, so we can say our V will be same for C1 as well as C2. So here it will be also V potential, and here also it will be a V potential, and obviously R is also same in the case. Okay. So therefore we can say the initial discharging current, let us suppose in the first case we assume that is our I1, in the second case we can say this is I2. Therefore I1 will be equal to our V upon R, and here also our I2 will be also equal to V upon R, which is non-zero. Okay. So we can say that option number B is the correct one. They are equal but non-zero. Okay? So from here we can say that our I1 is equal to I2 is equal to V upon R and not equal to 0. So option B is correct. Option B is correct. And obviously C is also incorrect because he said the current are unequal. Okay, option is A says that the current is 0, so A is also incorrect, and we need to check only now option D, and which states that C1 loses 50% of initial charge sooner than C2 loses 50% of initial charge. Okay, and charging or discharging, everything is same, will be only dependent upon the time constant, that is the product of this RC. Okay. So you can say that the discharging depends on time constant of the circuit, that is about tau, and this tau is equal to C multiplied by R. So we have two circuits, let us call this as tau 1, which will be equal to C1R, and we have our tau 2, which is equal to C2R. R is same in both cases, but we have our value of C2 is greater than value of C1, that is given to us, because this is 2 microfarad and this is 1 microfarad. So from here we can say that the time constant, our tau 2 will be greater than our tau 1. So it means our C2 is going to discharge with a longer time as compared to C1, or the reverse will be true. So you can say that our C1 loses 50% of its initial charge sooner than C2. Sooner than C2. So therefore option number D is correct. Option D is correct. I think this completes, yeah, so this completes these questions, and these questions were from the year 1986, 87, 88 and 89, and total there were 7 questions. So this complete all the 7 questions. Thank you.